In this unit, you will learn how exponential expressions and equations are used to model real-world situations like population growth, money, and decay. You will explore how exponential patterns work, how to write and analyze exponential models, and how to understand their graphs. By the end, you will be able to explain how exponential relationships change over time and why they matter. Exponential models begin with patterns. In this section, we will look at sequences and relationships that grow or shrink by the same factor over time. Term. A term is one number in a sequence or pattern. For example, in the sequence 2, 6, 18, the number 6 is a term. Geometric sequence. A geometric sequence is a list of numbers where each term is multiplied by the same number to get the next term. For example, the sequence 3, 6, 12, 24 is geometric because each term is multiplied by 2. Exponential relationship. An exponential relationship is when a quantity changes by the same factor during equal time intervals. For example, if a population doubles every year, it has an exponential relationship. To describe exponential relationships, we use expressions and equations called models. These help us represent and predict real-world situations. Exponential expression. An exponential expression is a math expression where the variable is the exponent. For example, 5 times 2 to the power of x can be written as 5 times 2 raised to the x power. Coefficient. The coefficient is the number multiplied by the exponential part of the expression. For example, in 4 times 3 raised to the x, the coefficient is 4. Parameter. A parameter is a value in a model that controls how the function behaves. For example, in y equals 2 times 3 raised to the x, the number 3 is a parameter and controls how fast the values grow. Exponential model. An exponential model is an equation used to represent growth or decay in real life. For example, y equals 100 times 1.05 raised to the t can model money growing by 5% each year. Exponential models can either increase or decrease. In this section, we will describe how exponential functions change over time. Growth. Growth means the output increases as the input increases. For example, money in a savings account earning interest shows growth. Decay. Decay means the output decreases as the input increases. For example, the value of a car often decreases over time, which shows decay. Increasing. A function is increasing when the y values go up as the x values go up. For example, the graph of 2 raised to the power of x is increasing. Decreasing. A function is decreasing when the y values go down as the x values go up. For example, the graph of 1/2 raised to the power of x is decreasing. Graphs help us see how exponential functions behave. In this section, we will focus on key features of exponential graphs. Y-Intercept. The point where the graph crosses the y-axis. For example, the graph of y equals 3 times 2 raised to the x crosses the y-axis at 3. X-Intercept. The point where the graph crosses the x-axis. Most exponential graphs do not cross the x-axis. For example, 2 raised to the power of x never equals 0. End behavior. End behavior describes what happens to the graph as x becomes very large or very small. For example, for y equals 2 raised to the x, the y values get very large as x increases. Asymptote. A line that a graph gets closer and closer to but never touches. As the graph keeps going, it moves towards this line without reaching it. This line helps us understand how the graph behaves as it goes on forever. Asymptotic behavior. Asymptotic behavior means the graph gets closer and closer to a line but never touches it. For example, 1/2 raised to the power of x gets closer to y equals 0 but never reaches it. To describe where a function exists and what values it produces, we use domains, ranges, and intervals. Domain. All of the x values that can be used in a function. For example, the domain of 2 raised to the power of x is all real numbers. Range. All the y values a function can produce. For example, 2 raised to the power of x only gives positive values. Interval notation. Interval notation is a way to write sets of numbers using symbols. For example, open parenthesis 0, infinity, close parentheses, means all numbers greater than 0. Finally, we analyze how fast values change and what limits a model may have. Average rate of change. The average rate of change tells us how much the output changes for each change in the input over a certain interval. For example, if a population grows from 100 to 200 in 2 years, the average rate is 50 per year. Constraint. A constraint is a rule that limits the values in a model. For example, time cannot be negative in a real-world growth model. Continuous. A continuous function has no breaks or gaps in its graph. For example, exponential models of growth are continuous over time.